Okay, bear with me, guys. I'm going to work a few things here. And, yep, just want to confirm something here. Good. So, we have to note, February 6, 2018 is when the inspecting engineer made a report. But today, I started on this at 5 a.m. and I've got quite some hours in this, believe it or not. And so now I'm redoing the video over and over again. And I've got about 2 hours of other videos, combined 3 videos. Okay, we jump into the article. You know, let's make a couple of statements here. Miami Herald, great that they're trying to get data out there, but they're getting wrong data out there. And when you get wrong data, it's terrible. You have to have a way to change your data. And this Miami Herald does not change with the facts. They just don't do corrections in their, in their articles. They also quote things like this. I'm going to jump around here. 3 independent engineers who examined the photos, records, and bridge blueprints at the Herald's request concurred the cracks were a red flag, just one, not S, red flag signaling potential critical structural problems. Outside experts have zeroed in on the trust members. And it's a link. You click the link. And what does the link do? It links you back to Miami Herald in their article dated March 15th, which brings you down to, and I'm going to get around to these bloggers, AVI, this person down here that they're quoting as one of the experts. When you made a comment there, you then make this whole thing an expert comment. That AVI is a tool guy, he plays with tools. And you date it back to a time when we have more data now, better data than we do then, than we did then. Now, let me show you a few things. One of the things is this article is going to be talking about is shearing taking place here. That shearing took place here. That it forced that this member was sheared here. Now I'm going to show you something awesome about this whole thing here. You see this breaking here? That's the underside of this breaking. Now it could have been when it's collapsed and crashed that this went up like that, but you would see some cracking too. But let's just call it just the lamination. We see no coating here, incidentally. But watch this. We're going to go to a few things here. This is what the article is going to allude to, that the shearing took place here. Let's just go to the article, and then I'll come back to that. And I went to the bloggers and found their information. And for me to do that, I have to come back to the article. And we come to the article. Identified in plans as number 11 as being under design. Well, you can't determine if it's under design because we don't know the full design of that. This is not strong enough to withstand the pressure. Now, you can state facts. I'm going, it's a fact that this number 11, is different design than number 2. And then I work with the data, the facts. The facts are this has post-tension members inside them. Cables, let's call it 1 and 2, and 3 and 4. The reason why I do that, this can be 1 and 2 reversely. This was completed first on the bridge, and then this is number 3 completed, and number 4 was the last one being worked on. Now I'm going to give you some quick teasers, and then I'll get back to it. Maybe this will keep you watching the video. Take note that these two are more divided equally in this member, 1, 2, and 3. And they're also anchored at the bottom. But then no one's talking about shearing happening down here. But yet they're talking about shearing happening here. I've grabbed this from the article. Structures is this engineer supposedly. And he's showing shearing here at number 11 in the deck. So the force is going this way, and you're able to create the shear because you're anchoring at this point, pulling with a downward force here. Well, for shearing to take place, you also have to move number 12 at the base. You have to move it. This is together. These are together. You just can't move number 11, creating a shear force without moving number 12. It's all connected. If you told me this crushed up and this was so stable that this crushed up and broke apart, yeah, but you have your shear line, which they all say in these bloggers. I've followed a few of them the past few hours, looking at them, reading them, and this is the contention. And to move this to shear, to move this, what do you have to do? Move the canopy first, which I've always said. The canopy has to move first, not this. You can't have this movement down here without having this movement this moving. And to move this, you've got to move the canopy, in which I've always said the canopy is the failure first. And to get the movement. Now watch this, what most of them aren't paying attention to. They all have this braking. Remember, a lot of people are always saying, why did this not fail down here? Well, it's a different design. Plus, we don't have the forces coming to the same here. And I'll show you. Bear with me here. But notice this. This is falling this direction. It's not just falling down. It's falling this direction. As we know, it fell off and it leaned over. As it falls over, it's pushing. It's literally pushing. A force is going that way. Look at the shape of this triangle, if you will. It's now leaning away. This is down inbound. So imagine this is this one. It's approximately here now, let's call it, but in relationship to this number 10. This is still pretty much in line. This is number 10 and the top of this canopy, and this number 9. They're about the same. A little slight buckling and going on here, but apparently, because it's ghosting, the video ghosted it. So we have faster movement here based on pixelation. That's photography stuff. Yeah, I already said that in another video. But notice this is pushing away. The top of number 12 in the canopy is pushing away. Because as this broke, this broke secondarily. The forces transferred down, as I told you guys. This then created a force going this direction. And it can only push so much before gravity and the dead load just made it drive downwards. So it shifted over and then dropped down. And you can see it here. And as it dropped down, it pulled. This is still attached here with some reinforcement, possibly the post-tension cables, the longitudinal cables. And as it came down, it pulled it, and then it pulled it back over towards this direction, back towards inbound. And as it came down, it created a hinged effect, breaking the base. So all this, you can see again, this triangle is pushing away, not that way. Hopefully you guys will see that. Here it is here. This is no longer upright. This is a triangle pushing away. And then as it comes back down, it pushes back. And, okay, so this is just, I'm sorry guys, it's just ridiculous. Now, with that said, if the NTSB determines that this failure happened here, I never had any respect for the NTSB anyway. So you guys, you know, they use fake videos. They don't use real logic. They don't answer to anybody, to the public. They don't take answers or questions. How did you arrive at that? They don't change their position. That's it. I'm willing to change my position. You show me something where you can show me that this bridge, that this one cable is capable of pulling over, you know, this much concrete, pulling this entire section over to create a shear here. I'll change my position. But I'm going to show you something why this failed up here. Why? I'm going to give you not a why, because I have to leave open for a mistake, right? For an error. So I'm going to show you why I think it failed, and you should love it. Okay, so now I showed you, you know, some new data here. Now, yes, as this is failing, this is buckling. I like to, and if this is something at all, then I'd like to even say, because remember, we have ghosting here. We're showing no member, so, you know, what's going on here could be, you know, nothing here either. So, and I'm calling it ghosting, a photography type term. This could also be just literally a puff of smoke from the floor drain, as someone said, or from the drainage of pipes or anything up there. Remember, this is a hollow tube coming down here in the post-tensioning member. Also, we have this banner around here. This could just be wind blowing down here by chance. Remember my post hoc thing. Just because you see one thing does not mean they're related. And that's the problem. They're basing everything off of this is their smoking gun, that this is the beginning of the failure, because they see no other, they're incapable of seeing any other failure in their mind. They need to physically see it for them to be able to visualize it. And that's with all these people that claim to be engineers, and some of them are engineers. You know, just because you see one thing, that doesn't resolve everything. Just because you see you understand what that means. No, why didn't it fail down here? It's a different design. Now you're going to like this. I'm going to give away the teaser. So we're back to the 1, 2, 3, and load path. So let's talk about load paths on almost anything. As you apply a load, say this was on the ground, right? It's a counter force also, but it's not just right here in this column creating a force going downward. It actually creates a force going like on a 45 also. This is its zone of influence, as I'll say commonly for you guys. right here and here. So if I was to take away dirt, in your theory, in a typical person's theory, it goes straight down. If that's the case, I can dig all this away right up to the side of it, and nothing will happen. There'll be no failure at all. The load's going straight down, so there's no chance that dirt will buckle out and force out because, well, there is no forces going out in that direction, right? I'm being facetious. Yes, I'm showing you that, yeah, you can imagine that the dirt, it would come away. Now, some dirts can take the forces depending what the forces are. Now, watch this. So this is in the center. Now, here's the kicker. Watch this. These are on the ends. And I've talked to you guys about the load back here, how the forces, how you can create buckling by tensioning this side and then on this side, create failure and then create tension here. But watch the load path again. So remember, I just talked to you about, come on, I'm trying to enlarge this image. Oh, I'm enlarged. Watch the load path. As these plates, I'm going to show you on this one, as this plate, the load path is coming down, and here's the concrete continuation of it. It's going straight up, and it's down the side here. It's 1/3 in, and the same thing with this one. They cross each other. I spoke about that in another video. The chaos mathematics of this must be crazy, but this force comes down on top of that anchor, in fact, which is then transferring load down to there, which is, well, wow, chaos mathematics for me. And it comes down. It's going down here, and it's continuing down the column concrete. Wait a minute, look, watch this one. Here's the bearing force. Now let's say it's no 45 at all. It just goes straight down because some people like the forces that can just go straight down and they can't visualize a force going at a 45. Let's just say these forces go straight down this column. What I'm showing here is that these are not all the forces, but I'm trying to give you a visualization, if you will, of how you'd have to balance this or post-tension these cross members with a delicate thumb, if you will, delicate handling to make sure you don't throw it at a imbalance while you're doing this cross section. You can also see that this is much different than the number 2 above at the blister section. That there's more cover, that the location of those post-tension bars being more centered as opposed to these being to the outside create a different force. Could be an explanation on why they had no issues with number 2 as opposed to number 3, as people would like to see why they didn't have an issue. Something as simple as that, something overlooked and as simple as that. Thinking for you guys. Thought for you guys. Watch, it goes straight down. Whoops, it's crossing outside of the canopy. Huh. And then it's coming back into the number 10 member, and then it's continuing down. I want you guys to use a string on this piece of paper on here, and on the drawings if you like, and you'll see that it clips the canopy right here. These forces do. Right about there is where these forces align. And you can do, if you could scale this, you would know how much concrete it's applying before it skips out of the canopy, and then it's required to skip back into the cross number 10 and back into number 11 again. But remember, forces don't work that way. They're going to come out on an angle. So basically, we're creating a chaos mathematics again. We're creating some weird forces going on here. Boy, oh boy. And then we got jackhammering around here to access something, and we have jackhammering. So they did not expect the flyovers or these images to be public because they thought this would be covered by a plate ultimately with the pylons. So we know that the flyover of the drones showed at nighttime showed these nodes they look like this, and no one does future knowing that you got to come back in there and work on these post tensioning members, make it look so raggedy. So I think they did have a nice formwork set up there, knowing that they had to come back and detension because the plans say they should detension. Or they forgot to put the form on there around these guys, and then they went back in there with a jackhammer and resolved it that way with a jackhammer. While we're here, we're going to address this long rope here. This long rope is the lanyard for the men to support themselves on. If you look at the end of structure down here. If you find the end, you'll see that they have the rope around the structure, and also a protection for the rope and pipe so the rope doesn't cut itself through. Okay, let's go to this 2016. These are the plans dated 2016, and I'm going to come back to this. And we go back to the Herald. The Herald is not they don't have very good reporting because they do all this public information stuff, releases, and yet you can clearly go to FDOT's website and find that based on the this bridge starting at 623 down to the plans, that the pylon location meeting, they had a pylon location meeting, and the result of that pylon location meeting dated October 31st, 2016. If you come down to bullet number 2, the overall required additional width was determined to be 12 feet, no longer 11 feet. There is no addition past this. Let's change this to that. We changed it now to 11 feet. So the Herald is bad data for you guys. That's awesome that they can force data out if there are with the lawsuit. If the lawsuit was resolved, which I don't think it was. I think okay, in this screenshot, if you will, take note of that. The rods were apparently a modification to the plans added to the bridge design after FDOT asked FIU to move the engineered bridge 11 feet north. Well, this is a wrong quote. FDOT never asked for 11 feet to move it. It's 12 feet, as I showed you in the previous clip. Also, if you read below the highlight, these same engineers in part of this article, they also stated that the transporter being too close to the roadway on the canal on the bank would be an issue. I stated that in a previous video that would be an issue, and that's why you'd want to bring them more inbound and away from the roadway edges. Including managing development of design, permitting right-of-way, acquisition approvals, and easements design. I'm just going to read on. It all falls under FIU's permitting authority. FIU is ultimately the one responsible for everything that happened there. They're supposed to be there, okay? Reading on. They're supposed to resolve all of this. Data collection, methodology, all of this stuff is FIU. FIU, FIU, FIU. Here are the dissection of the nodes. Again, we see a cross section of this AA, and we see this, if you see the load path, it is clipping the edge of the outside forces, or clipping the edge of the in this blister, the outside forces. Then we have forces crossing each other here, which is just crazy. This is just chaos mathematics. You guys should really look it up. That you've got this force coming down, this force coming here. The meeting. What are they doing on these members? What are they doing all together? We only have 1 foot of canopy thickness. We're at the edge of the canopy thickness right here. If you follow this plate, it's at the very edge. It's a force is like right in contact with the edge. It's no buffer, if you will. It's immediately having a contact point load immediately. I have to give it that space. It's not immediate. It's within whatever the space is that 1 inch, inch and a half of concrete there. So I'd have to add that to the additional cover of the 1 foot here. Then you also have the voids of the transverse, and this is the rebar, reinforcement coming across this load path, which I actually say creates a void. Not something that it can work against you. If you have the reinforcement right on top of this, well, then you have nothing. Ideally, you want your reinforcement down here, depending on where the forces are. I'm done with this. Clip this image there, because that's open for negotiation on my part. Here's the canopy. Oh, they may look big and beefy. There's the blister. The canopy. We're only talking 1 foot. Then we add in two 2-inch conduits, which are placed right alongside the load path of the post-tensioning member of the plate, of the top plate, that big huge plate you guys saw here. This guy. This plate here is a plate that's down there. It's a huge plate, and it's capable of transferring the forces downward. And if it's right here, let's call it right about here in line with the outside of the column of the diagonal, it's right here. Right next to it is another void, 2 inches, total of 4 inches. All right, so that's going to eliminate this thick. If we're 1 foot, this thickness. If it's 1 foot thick, now we've got the 2-inch void here, and that's 2-inch OD, outside diameter. Might be ID. I don't know which one it is, but it doesn't matter. It's 2 inches. If it's ID, oh, it does matter, but it's 1 foot 2 inches off center line, so you could actually figure out exactly where this void is if this was placed in where it's supposed to be placed. But as we know, this company, MCM, has a placement issue, so it could be even closer in. So our cover here above this 2-inch is now so to make this fail, all I got to do is break this little bit with a hammer. I can hit this little bit. Now I'm down to 2 inches plus this, say 2 inches of cover. All I got to do is hit 2 inches. A walkway. Your walkway and your sidewalk out there in your backyard is about 2 inches. Back if you have a house built in the 50s, they pretty much did 2 inches 2-inch walkways. 60s in the city houses, 50s rather. 2 inches, nothing. One jackhammer strike, you're done. So we're 4 inches. Now we're down to 8 inches of concrete right here. This also creates a force. Since it now wants to hang down, you need counter forces because it now wants to create forces inside this area also because of its weight. It's got a weight on the outside. It needs to be resolved with tensioning, with tensile strength, with the reinforcement, all coming back here. Again, I'm not going to go down this path. I'm showing you chaos mathematics. That is just craziness. Okay, where am I with this? The contractor, I think we talked about this maybe in a previous video that I don't know if I posted, so sorry if I'm redundant. I'm going to talk about this again. I'll pause it. You guys can read it. They did deal with reverse. No, I guess I didn't slide it over, so I still have to deal with this. So allowable temporary stresses and deflection. This is for the SPMTs, or moving company that would move it. They typically are supposed to be involved in the engineering as recommended by FDOT, to be involved in the engineering of the structure, so they can then tell you what the forces will be and why they need to be involved, because their machine's going to create a contact points that need to be reinforced in such a way that FDOT structural members will likely see stress reversals that may be detrimental, and they actually do not want you to do to have this. They do not want you to create a temporary stress, meaning adding post-tensioning to numbers 2 and 11 to counterforce these reversals. 4.6 allowable stresses and deflections per this right here, FDOT statement here. They will supply soft support for the bridge. In this case, it was wood cribbing. Moving on. They do not want you to do counter forcing is what this amounts to. The contractor should provide analysis for jacking, moving, and erection of loads to ensure the temporary stresses and deflections are within allowable values for the bridge, and that the bridge is adequately reinforced to handle the calculated temporary stresses without cracking. Notice that, without cracking. But they use the word should here, meaning should is not must. Okay, should is not must. And this is terrible that FDOT gives a should here. Temporary overstresses of the bridge should not be allowed during lifting and moving. Temporary overstressing of the bridge. So this means that number 2 and number 11 are not designed, or should not be designed, and I say should not because they say should, and it's terrible, should not be designed for temporary during lifting. The meaning number 2 and 11 was not for cantilevering effects of the bridge. That's what, again, why I think well, if it is, it should be considered wrong. Get it? Should. All right, I'm done with that one. And I think it's more for racking. Okay, we're actually wrapping it up now. We're getting faster on this one. So back to 12/9/16. That was the original date of the plans after they did the 12-foot expansion. Why 12 foot? And this shows why you should not follow this as science, if you will. And I'm biased. I think the NTSB is... they do terrible reporting. Again, they don't answer to the public. They don't answer to anybody with knowledge. They don't answer to anything that you may ask. They just say, here's what we say the facts are, and this is how it happened, and then they disappear into the woods. Well, wow, you're talking about trolling. So, I mean, that's some trolling stuff. And if you look at their videos, how they do the reports, they use animations, and then there's never a question about animation. Wait a minute, your animation shows the two buses coming together. They don't say what happened beforehand, and then they show the one bus goes off the bridge, and you say that's it. Okay, and even when they do their data, like the Iowa Bridge study, because I have researched NTSB's studies, statements, and when they do it, they're not open for negotiation, even though they throw under the bus clearly that the federal government had a say in the changing of a node. Then they don't blame the federal government for their participation. They just blame the bridge builder again. Really? Okay. Our weakness. So cracks in concrete are 100% failure. So if I were to crack a sidewalk, 4-inch sidewalk for you guys, it's 100% failed. The only thing that's holding it together at that point is the earth underneath, if there's earth underneath of it all. If there's reinforcement across, let's call it rebar, or holding the two together in plane like a dowel. And its tensile strength is holding it together once you put loads on it. And the loads are dead weight also. But as you go from one side of the crack to the next, as you approach the one edge of the crack with the load, you're putting that dowel, that rebar, under shear. It wants to break between the two cracks. The concrete's no longer acting, the rebar is not in tension at that point. If you can follow where the load is, say a car tire underneath that sidewalk, right below in that side that the sidewalk is on, that little bit of rebar, yeah, it's under tension under that tire. But where the two cross, where they're crossing, it creates a shear moment. Now that's important when I go back to the other videos, images. There's nothing they could have done. There's nothing they could have done short of starting over. You know what? I said in another video, I kind of agree with them on that one. They need to know that if these cracks were not predictable, which they are predictable at intersections, cracks predict. That's one of my videos where I'd say, wow, you know, how did they handle all expansion in this? Because they've got so much going on. They have so many lifts, concrete pours. Yeah, pour here. This creates a joint between these. These have a joint. These truss members, if you will, or webbing. You know, you can call them too, one of these truss webs. They have a joint, cold joint, and they have a cold joint here between the deck and the canopy. And then they have cold joints at the blisters and the canopy. And who knows where else they poured. And they have joints wherever the grouting is, wherever grouting took place. And anywhere else they poured another pour. Coming back to this one. This is clearly not been jackhammered into. This is the tooling. There is the lanyard coming from here all the way across. It was not held up by any crane. You know, they use the lanyard. Why would they hold themselves up by a crane that could move and tear the man apart if he was still connected to the crane? This is the article that over here that they're referencing, where I mentioned in another video that the attorney had an agenda releasing that article ahead of based on the dates, but because they could release everything from February 19th, and he released something dated February 26th. And I said, well, and I even made in one of my videos, I don't know if I posted it, or maybe it's the last one where I said well, you know what, he could tie it in because it is related to the February 6th. This letter is related to this February 6th, 2018 documentation here of the cracks. So I extrapolated, you know, he could reach, but it appears he wrote and said that, no, I didn't mean to release that part. Whatever. All right. But he also wants to control the narrative, as I said in the previous video. As always, I receive requests for public records. Please forward it to the Office of General Counsel. He's a General Counsel. He is. He's saying he wants to be the go-between, the filter. As permitted by the NTSB, we will continue to provide updates when additional information becomes available. But, of course, there's way more letters than this that he can release. He did this on the narrative. I'm sorry. My opinion, he did this on the narrative. Okay. And let's see what his response is current day about this article. And we'll go back to that to see if he did release something. There's nothing they could have done short of scrapping it. His whole design, sorry guys, again, I've been up since 5 a.m. His whole design is scrapped because I think the ratio is wrong. And it's just, come on, this is just something they should have tested. It'd been fun, you know, close the road off, test it, and then go, cool, that was kind of cool. It would only cost us $2 million to test that. You know, the whole build project is $19 million, I think, but this is probably, they got maybe $2 million in this. Like, cool, that was cool. Okay, that design sucks. You know, and the school writes it off and throws it in the trash. You know, and really take it apart and work on it and go, all right, what did we learn here? This is what the thing is, the crime. We could really learn so much. A third engineer consulted by the Herald, concurring with the first two, but asked not to be named. Okay, concurred with these two. The first bridge engineer, Ralph, this person of Naples, said the cracks did not appear significant to him. So cracks are 100% failure. Cracks are always significant. And this person saying this engineer, boy, he's just put it in written form. Cracks are total failure in concrete. There's no, oh, it's expanding. It's gonna, when you let go of the stresses, it'll go back together. The cracks will go back together, and the concrete is one again. It's 100% one again. This is just ridiculous. You know. Yeah, and people who write analysis using numbers, well, this was used numbers, all right? They use numbers on all of this. The analysis on this with FIU, with FIG, with all of FIG's, Denny Pate's access to all his engineers, with FDOT's engineers, with the federal government's engineers, with every engineer that touched these plans beforehand, with all their knowledge and skill set and ability to do math. None of them saw this failure as they see it here, especially at the time of this post-tensioning. None of them saw it. So that's all math. But they lost common sense. They wanted to push the limits, as most bridge engineers want to do. And the bridge engineers have a thing about, I want the longest span. I want the longest span. It's always the longest span with them. This right here. This load path simply right here. That when they were creating this pressure here, this load path came across here, went outside the deck, went back into the deck at number 11. And when I say back into the deck, it did not go back into it didn't cross into air and come back. The forces are then concentrated here. This created a crack. So this is cracked. The forces are coming down this cable as a plate. This is the chaos mathematics I'm explaining to you guys. You got forces coming down here, and you got forces here. Both of these forces combined create a weakness right here. Both of these forces combined create a weakness right here. These two crossing each other. Both of these forces combined create a weakness here and here. So now when you look at this, put this in a circle, and you see all of the chaos mathematics here, you actually see that, what do you see here? This actually is right at a joint. This is at a joint. This is above a cold joint. It's just so many things that the forces, when they're crossing, are these forces creating a downward force right here then? Which makes it so easy to cause failure. And then you have a force crossing here. Again, failure. There's so much that says failure here with this interaction that I can only come to the canopy failing first. This rolling over, I'm not going down there. Hey guys, thanks a lot. Sorry about the long video.